Always clearing my throat. I want to do a video very quickly on the idea of geodesics. Geodesics was developed very early in differential geometry in order to find the shortest distance between 2 points. Shortest distance between 2 points is a straight line, of course. But now let's imagine that there's an obstacle on your path. Now there's a straight line, say, around this armrest. You know, I wouldn't want to go over it. I'd want something more gradual to negotiate through. And if I look at that, it will be the straightest line possible between the 2 points, taking into account I have to go around the armrest. So it was when differential geometry was starting out that you had to negotiate around mountains and hills and valleys and find the straightest, shortest path between 2 points. This also bears into general relativity because you have to negotiate a geodesic through space-time. Now in 3 dimensions we can imagine all kinds of curves through space and imagine all kinds of different loops and spirals and whatever manner of, even straight lines that we can imagine through space. But none of them would be correct because they don't take into account the 4th dimensional curvature of the nature of gravity. So these new geodesics need to be the shortest, straightest paths taking into account these 4-dimensional curves. But how do you determine shortness and straightness when you can imagine all kinds of lines, some which maybe, like if I had a gravitational mass here, I could imagine a straight line above it, but that's not the geodesic. The geodesic is curved because that's the only path that an object can move through. That's the curvature that must define the nature of the body's motion through the gravitational field. So the idea of straightness in these curved space-time membranes, if you will, I'll just call them membranes just for fun. How do you determine shortness and straightness? We need to try a thought experiment now. Imagine 90-degree turns. We're going to start out walking. I can walk forward and just make a 90-degree turn very quickly. My path is not very straight at all. Now I want to imagine that I'm doing it on a bike. Well, now my path is a little bit more straight, isn't it? Because I have to negotiate the turn instead of just turning on a dime like I can when I'm walking. In a car going 60 miles an hour, now the turn has to be greater. It's more straight. It's getting progressively more straight as I go along. It's still curved, but the curve has to account for more space because my body wants to continue going forward at increased velocities. This is the principle of momentum. You can carry it forward and forward and forward, onward and onward. My momentum, as it increases, I will have to take a more and more straight path to my destination to make that 90-degree turn. If I'm in a spaceship going half the speed of light, for example, it's going to take a great, long, wide turn. And overall, it will be a very, very straight path as I go along on my very wide turn. So there's this connection between straightness and momentum. So we need to imagine the most momentum possible for an object to determine a geodesic. That is the best that we could clearly do. If we had the most momentum, we could have the straightest possible path. The answer, what would it be if I didn't have the board, right? The answer came about in the relationship of a particle's mass to its energy. E squared equals mc squared plus pc squared. P is your momentum, and momentum is expressed as your mass times your velocity. This is the total energy of a body, particle, or a mass. And we have to take into account the very specific case of a photon. A photon, we'll say C is equal to 1 for this so that we can geometrize it, is the term. If C is equal to 1, then both these drop to just m squared and p squared. And with m now for a photon, mass is 0. So we can say that this term is 0, and that E squared will equal p squared, or energy equals momentum. For a photon, you have the highest possible momentum for any particle. And since your momentum is at maximum, therefore, we can claim that this is the single least curved line you can possibly travel on. It's the straightest possible line you can assume. Now we need to talk about a black hole for a moment. Because above the black hole is what's called an event horizon. And what is an event horizon? An event horizon is a light-like geodesic that comes around to itself. It's a light-like circle. Light can move on this circle forever. It can never go below it. It might be able to radiate above it, called Hawking radiation, but it can't do it directly. It has to radiate above it through call it an orphan particle. One comes in and it irradiates the photon and the other escapes to infinity. That's Hawking radiation, but we won't discuss that now. So what we have above this black hole is a light-like geodesic. The straightest possible path any particle can take is a circle above a black hole. And yet, physicists today will tell you that no, a particle can assume an even more curved path than that they will fall through that circle and fall into the singularity. This is counter to everything else in general relativity. And I think any physicist you ask and you give them this example, they will tell you, yes, that is counter to everything we claim in general relativity. But they have to acknowledge it because the only way for a singular black hole to exist is for things to fall through a light-like geodesic circle into the singularity. As it's falling through this light-like geodesic, becoming more curved than the light-like path, it's actually supposedly moving backwards through time. Which gives the strange question as to how black holes grow, because that would mean that the particle would arrive at the singularity before it even entered. This is an element of the Hawking paradox. And the resolution to this is absolutely simple. You simply say, the singular model of the black hole must therefore be incorrect because it incorporates greater curvature for geodesics than the event horizon above the black hole. If I have a smaller circle inside a larger circle, then this circle must have more curvature. And if this circle is a light-like geodesic, that means that this circle cannot exist. What is going on instead is that mass collects around these event horizons. And suddenly there is no problem with geodesics. And suddenly there is no problem with black holes growing. And suddenly there is no problem with particles falling into under these event horizons and going back to the singularities, and then therefore growing the black hole before it even ever came into it. None of those problems now exist. And then when you say, okay, no geodesics that are more that violate these principles of the event horizon, then you simply say a non-singular black hole. And as I've said before, this is easy. The next part is hard, because if you have an event horizon that's open, you then have to incorporate Einstein's theory of the Einstein-Rosen bridge, which can connect distant points in space and time. And in doing that, you now are simply debating the ramifications of my hypothesis.